All right, folks. Happy Friday. Hope you guys are having a good week. And just an update from Burlington, it managed to snow this morning. So you're not missing anything up here yet. Anyway, today's lecture is kind of short because I've been asking a lot of you this week with an exam and other assignments. And I don't want to overburden you time-wise. So this shouldn't be too long. But before we get started, just logistics again. All right, so a reminder, if you have not done it, exam 2 is due today by 5 p.m. That includes both attempts on the multiple choice test as well as the survey for the memes that your classmates have submitted. And you got to do that by 5, okay? So please, if you haven't started it today and you're starting to watch my lecture, which is posted at around noon, maybe you should stop watching this lecture and then take the test. Anyway, but then of course come back for my lecture. Anyway, okay. So in addition to the exam being due Friday, a couple of due dates for Sunday, this Sunday by midnight, is the lecture quizzes from Monday this week and today. There is no quiz for Wednesday because that was just instructions for the exam. And then you also have chapter 14, which is about flooding. That reading quiz is due on Sunday night. Okay. And then I will also just let you guys know that I've posted another submission portal for more memes. So as you guys saw, there were some really good ones, and I will do something similar in the future. And once I have all the survey results from people who have taken the exam, I'll let you all know what the final winners were for those memes, okay? And then just because it's that time of year, and if you are a senior, congratulations, this is irrelevant. But if you are not, and particularly if you are earlier on at UVM, like a freshman or sophomore, this is a time of year where you can begin to register for classes. And so if you liked Geology 001, even amidst our crazy quarantined version of the class without field trips, which is sad, there are more classes that you can take, and they are good. So there's 3 classes that, because you've taken Geo 1, you can take in the geology department. And the first one is Geology 151, which is geomorphology, and that's with Professor Bierman. And basically, the whole question that class asks is, how does the surface change through time? And I'm a geomorphologist, so this is personally my favorite topic, but it's things that are processes you can see on Earth's surface, so things like glaciers, erosion, soils, rivers, changes in tectonics. This is a cool class. Professor Bierman is a really great teacher, so I strongly recommend that you take that one. Another great class you can take is Field Geology, Geology 101 with Professor Kleifus. And this is a great class because it is completely field trip based. And the main point of this class is, how do you recognize geologic history from field observations? So you'll get in a van once a week and you'll drive out to some really pretty spots around Vermont, and you'll learn about how geologists can take evidence from outside and then stitch together this history of the Earth, just from little observations that you make in rock outcrops or across the landscape. Really fun class. And then another class is Geology 185, Geocomputing with Professor Nico Perdriel. And this is a class where you will gain a lot of hands-on skills with different computer software that geologists use. So the main one is GIS, which is a way to organize spatial data, and you'll learn how to make maps. You'll also learn how to do some rudimentary coding, which is increasingly a life skill for a good career. So these are all really good classes that you're all qualified to take now that you've taken my class. You have enough of the background information on geology that you would be successful in any of these classes. And if you have any questions about the geology department and what classes you can take, or if you are interested in becoming a major, which would be awesome, you should contact Professor Linney at alinney@uvm.edu. I will also post a link on the Blackboard to a sort of like geology hype video that our department made that explains why taking geology at UVM is a great experience. So anyway, just to stay on my soapbox about why geology is so great, here's some reasons why I think you should take more geology at UVM. Is that, you know, so long as we are not stuck in self-isolation quarantine forever, there are many opportunities to do field-based learning. This means you get to go outside to do schoolwork. There are opportunities once you take more geology classes and get to know professors more than just like being in these big intro classes. You can have opportunities to stick around for the summer to do research, sometimes to do fieldwork, and eventually, if you're really interested in it and become a major, it'll help you develop a way to do a senior thesis. But looking beyond just UVM, a reason that you may want to consider doing geology as a major is that you have a pretty good career path set in front of you. And I think one of the most important things that here's a life lesson for you, all you youngins, is that the most important thing that you'll ever learn about wherever you work is who you work with determines how good the job is. If you don't like who you work with, you're not going to like your job. And I have never met a geologist I didn't like. So in some ways, I would say that, you know, geologists are down to earth, and you know, people who are just generally interested in being outside and learning more about the world. So I think they're great people to work with. But some other reasons that maybe just beyond the interpersonal level is that these can be fulfilling career paths. You can go on environmental consulting, particularly here in the Northeast, where you can learn about how to mitigate and clean up contamination from human activities, pollution, as well as like really work on a variety of really cool geology projects. I've talked a little bit about how I've done this in my life as a consultant, but you know, I got to live on the rim of the Grand Canyon for 3 months doing consulting. I got to go hike around in the Rocky Mountains looking at old silver mines for a summer. And I also went to places that, you know, you may not feel like you have any reason to visit, like the Dust Bowl region of Texas, because there's a lot of oil and gas there. But it's a really interesting career path. And then if you're not interested in the, you know, industry side of it, there's state agency jobs for environmental protection and public health to help states develop regulatory codes, or also making sure that businesses or organizations or even other government organizations are staying within the law. There's also on the horizon for new sort of high-tech jobs is that having a geology background is quite useful in remote sensing. So we're working with satellite data, GIS mapping, basically in data science. As a geologist, you take information from the world all around you and you interpret it and act on that information. And that's really what data science is collecting data from around the world from different sources, interpreting it, and then telling a company or telling an organization what to do. And then there's always the opportunity to do research like what I do. And you guys, if you're interested in that, you should definitely talk to me. And then finally, like one more reason that I think it's a good idea to take more geology, even if you are not set on being a a major or a minor, is that the more that you learn about it, the more enriched your experience is everywhere you go. So the more that you travel around in the world and maybe go to glacial places, you're probably just going to hear Soldier Boy tick off in your brain going, you, every time you go to somewhere that used to have glaciers. So the more you learn about it, the cooler places are when you visit them. So along those lines, let's jump back into our lectures, and we'll go back to sedimentary environments and different types of sedimentary rocks. So in the last lecture on Monday, we talked about terrestrial sedimentary environments and how those are the sediments that are formed on land above sea level. The main bulk of sedimentary rocks that we find in the geologic record that are being deposited are those that are in the marine environment. So there's a few reasons why this is. First is, well, most of the Earth is covered in an ocean, right? 70% of the Earth is covered by water. So most of the sedimentation that is going on Earth at any given time is going on in a marine environment. And because it's out in the marine realm, this stuff is going to be saved for much longer than sediments on continents. Because when you are above sea level and you have mountain building events or rivers that plow through or glaciers or whatever, you erode sediments. But once you deliver that sediment out into the deep ocean, it's going to sit on the deep ocean, turn into a rock, unless it is subsumed and consumed by a subduction zone, basically. So we have several different types of marine sedimentary environments, and we'll start with the one that humans are most aware of, okay? All right, so the ones that we are most familiar with are deltas. Deltas are where rivers that are carrying sediment meet the ocean. As that river meets the ocean, the energy of that water disperses and it slows down, and now sediment is going to fall out. I'm having an issue here. I'm missing a slide. That's weird. Well, one of my slides got deleted. Bummer. All right. Well, here's the bulk of what I was going to say, is that as rivers build out, all right, sorry about that. I had another whole slide in my deck and it has disappeared. So I don't think it'll be too big of a problem, but I'll jump back in, is that deltas are where sediments are dropped off at the boundary between freshwater rivers and the ocean. And what is really important about river deltas is that this is where much of human civilization chooses to live, right? So the most famous river delta that we have in the United States is the Mississippi, right? This is where New Orleans is, and the Mississippi River Delta was sort of this portal into the middle of the North American continent for European colonizers. And the deposition of sediment from the Mississippi River out into the ocean has remained important for sustaining this area of land. But then other parts of the world, right? Billions of people live in areas where rivers are depositing sediment. And Bangladesh in southern Asia is a country that is completely dominated by river deltas. This is where the mighty rivers that are draining the rapidly uplifting Himalayan mountains are building out towards the Bay of Bengal. So here in the entire country of Bangladesh is basically one giant river delta, where you have all of these rivers that are coming in and then radiating out and depositing sediment out towards the Indian Ocean. And then among the more famous river deltas anywhere else is the Nile, right? So the Nile River Delta, it's a complete desert area, but the water carried by the Nile from the highlands of Central Africa towards Egypt, right? This has created a fertile plain along the riverbed, which then when it reached the Mediterranean Sea has been depositing sediment out in this perfect delta shape, creating this like green oasis amidst largely sand and rock in the Saharan desert. But not all rivers create deltas, right? So the other, another really famous river in the United States is the Hudson River in New York City, right? But New York City is not built on a river delta. So why is that? So this is a really great short video that I think captures this question well. Why do some rivers have deltas?
Divided into two kinds of people, those with innie belly buttons and those with outies. Rivers also have innies and outies, not belly buttons but mouths. Where rivers flow into the sea, the land either pokes out or bends inward. But rivers don't have umbilical cords, so why do they have innies and outies? Well, coasts are the front lines between two opposing forces, land and water. In order for the ocean to invade the land, sea level either has to come up or the land has to sink down or be eroded away. And in order for the land to advance into the ocean, sea level either has to drop or the land has to build or be lifted up. Obviously, if sea level drops and then rises back again, there's no net gain on either side. But things get more complicated when a river joins the battle. For example, during the last ice age, sea levels fell by over 120 meters, and rivers cut deeper and deeper valleys to reach the falling seas. Then, about 18,000 years ago, warming temperatures began to melt the ice, and the now rising seas flooded river valleys around the world, creating giant estuaries and giving us the innie-riddled coastlines we have today. But when the steady landward march of the seas finally began to slow about 7,000 years ago, the coastlines around the mouths of some rivers began to gain back some ground. The key factor was the sediments that rivers drop as their currents slow at the entrance to the sea. Where the sediment supply was big enough and the ocean was calm enough, the dropped dirt piled up, eventually forming new land that both lengthened the river and divided it in two. Dirt would continue to drop out and build up at the mouths of both channels, splitting the river again and again and again, creating a new lobe of land advancing slowly into the sea. Thus, the world's great outie river mouths, the fertile deltas like the Nile and the Yangtze that have helped foster human civilization since its birth, all came into being at just about the same time. The same can't be said for all of the world's outie belly buttons. What can be said, though, is that innies and outies, for both rivers and people, are a small record of how we came to be. A huge thank you to the following organizations, all working towards...
All right. So, when we think about sedimentary processes along the margins of continents and the oceans, we are really thinking about what is controlling erosion and deposition and transport. And so, if we go to another coastal environment, right, we are getting away from where maybe a river is discharging sediment out into the ocean, and now you have water currents, surface ocean currents along the ocean shore, which are circulating and changing where sediments are deposited. And so if you have been out to the beaches in Los Angeles or along the coast of the eastern United States, sometimes you'll find jetties, right? These big piles of rocks that are set up along the beach, like, every, maybe half a mile in some places. The reason that you build these is because the coastal currents of wind pushing water onshore and then the waves coming back into the ocean move sediment down along the shore. So here in Santa Monica, where, the land of really great beaches, there are all these jetties that they have built, right? These little piles of rock. And they are built to catch the sand that is being moved by the coastal currents And as it's caught at that boundary, it piles up and it gives us distinctive sort of like stepped shape. So another thing to think about with coastal beach sands is that, you've been to these beaches before, right? You know sort of the sediment types we're talking about, right? It's sand sized. It's usually pretty well sorted, meaning it's usually just a narrow range of grain sizes that you find. And eventually that will turn into something like a sandstone. Now, shallow marine deposits. Let's go a little bit further away from the ocean or from a river delta. And this is where we have water depths of less than 10 meters. So in these environments, you still have light from the sun that penetrates through the water column, right? That light has not been diffracted away into the darkness. So here, this is still a vibrant ecological area. And we can have two different types of shallow marine environments, and it's based on whether it's clastic, meaning fragments of rocks, or carbonate, it's chemical precipitate. So in clastic shallow marine deposits, we typically have very well sorted fine grain sizes like siltstone and lots of shallow marine fossils. But the important part about a clastic shallow marine deposit is that there's a greater sediment supply, right? It has to be close to some sort of river system that is bringing new fresh sediment out into the ocean to be deposited. In carbonate environments, which are typically found in pretty warm subtropical, tropical areas where you are far enough away from major sediment sources and you still have a lot of nutrients, you develop these beautiful areas of carbonate platforms where coral reefs and organisms that make shells out of calcium carbonate will build up platforms of carbonate rocks through time. So the reason that, you can look at sediments being deposited off of a big river like the Amazon River, and that would create a clastic shallow marine environment, right? Because there's a ton of sediment load coming into the ocean. But all of those pictures from the Caribbean and the Bahamas, like at Fire Festival, when there's, all that clear, beautiful water, some bad sandals resort ad, right? Okay, it's really pretty because there's no sediment load in the water, right? You are seeing the white color of the carbonate platform underneath the water surface. That's why it looks so pretty. Okay, so I also wanted to show this. Wanted to show this time lapse of just to show you how much sediment is moving out through these basins. Okay, so this is the Amazon, like I was showing earlier, right? So what the purpose of this is to show that there is a lot of fine-grained sediment being moved out through the Amazon towards the ocean, right? And you can see it as the brown, muddy water. That's going to form extensive siltstone deposits offshore of where the Amazon is, right? Versus if we go to, the Bahamas, right? You don't see a lot of cloudy sediment. You just see that beautiful, like, aquamarine color because you are seeing the color of the water, the blue water, with the white carbonate platform underneath it, right? So this type of shallow marine deposits or based on the type of shallow marine deposit, it's actually quite useful in reconstructing like what used to live there, right? Because animals on the seafloor are very sensitive to the water depth because the water depth will control how much sunlight reaches the bottom of the seafloor. Then it also controls the other types of organisms that live above them that die, and then other organisms on the seafloor filter feed off of them. So we can use shallow marine deposits as a really useful tool to help us reconstruct what type of ecosystem was present in the geologic past, as well as understand changes in local sea level. So this is a tangent but related, is that all the major coral reefs in the Caribbean, as well as in Indonesia and Australia, we look at those areas where we have active tectonic uplift of some islands that have carbonate platforms forming, and that actually allows us to track with a lot of sensitivity changes in sea level related to the growth and retreat of ice sheets around the globe over the last few 100,000 years. So these are really useful sedimentary deposits for a variety of reasons. Okay, but then let's go to where most of the sedimentary processes on Earth are occurring, is in the deep moraine realm, right? So along the continental slope, as well as the continental shelf, or the abyssal plain rather, sorry. So here's the slope and here's the abyssal plain, right? This makes up most of Earth's surface, okay? So the type of deep marine deposits that we get is we get turbidites, right? Those big submarine landslides that flow out onto the bottom of the seafloor, right, along the edges, and then very fine-grained sediment that's floating around on the surface of the ocean that then gets deposited, or whatever is living in the surface ocean. So plankton like diatoms, which are made out of silica, or coccolithophores, which are little floating organisms made out of calcium carbonate, or foraminifera, which is a single-celled organism made out of calcium carbonate as well as silica. And these get deposited in deep marine sediments. And because you're really far away from any sediment sources out in the middle of the ocean, the rate at which this sediment accumulates, right, is very, very slow. Only meters of sediment per millions of years, or put in a more understandable unit, is like 0.0001 centimeters per year, right? So barely anything makes it down to the bottom of the seafloor. But over time, over millions of years, tens of millions of years, we get incredible records of changes in the oceans that tell us about changes in life on Earth, as well as changes in climate. So once these rocks lithify, or once these sediments solidify, it turns into shale, or into chalk, or another fun one called diatomaceous ooze, if it's made primarily of diatoms. And what's really interesting about the deep marine environment is that we have many sedimentary rocks exposed on Earth that are from the deep marine setting, but compared to our ability to observe, other sedimentary or geomorphic processes or geologic processes on land, we know almost nothing about what's going on in the deep ocean, right? It's 4,000 meters deep, right? Over 12,000 feet. It's incredibly inaccessible for humans. We can't see it, right? So we rely entirely on, a few missions with submarines to go down to the bottom, or mapping it out remotely with geophysical instruments. So what's interesting about the deep marine environment is that, this is still the frontier of Earth science in general, is that we really don't know much about the deep ocean. Okay, so sedimentary basins, all right? So sedimentary basins are basically anywhere sediments can accumulate. It's a hollow, it's a depression on the landscape. And a sedimentary basin is controlled by two competing forces of uplift, where land is being pushed up, and subsidence, where the depression is getting lower, right? So the balance of uplift and subsidence and changes in uplift and subsidence through time determines how and where sediment is transported and deposited in a basin. This concept is extremely important in the search for fossil fuels, because if you can scientifically reconstruct how a basin evolved and filled in with sediment through time, you can understand where you might find hydrocarbons, right? So this is a little bit hard to see, without having some sort of physical model. So here's a stream table experiment that shows this pretty nicely. Okay, so this is like in someone's lab where you have basically a fake river filling in a basin with sediment, right? What we're seeing here is the erosion and transport of sediment downstream, and then the formation of a delta, right? And some of that fine grained sediment is making it further out from the delta. What you are seeing here, right, is how this basin is evolving through time. And if you change how high or low the water level is, you change how far out or far in sediment is deposited. So when I talk about basin evolution, right, we're talking about this control in basically where the water level is. So what can control the geometry of the sedimentary basin, right? So it is primarily tectonics, okay? So there is basically one way to think about this is wherever you create uplift with accompanying subsidence, you are going to create a valley or a depression or a basin. And that is a natural point to which water and sediment are going to flow, and it will fill up over time. So in a collisional tectonic environment, such as like where two continents are running into each other, the weight of the mountain belt, right, that is being uplifted here is going to cause subsidence along its margin, right? Similar to how when you load an ice sheet on top of a continent, you depress the crust and you can create lakes around the edges, right? When you create a giant mountain belt, which has a lot of mass, it depresses the crust around it and creates a foreland basin. If you have a continental rift where plates are spreading apart, right, you are creating natural low points. Those low points are going to fill in with sediment, okay? So here, where the crust is pulling apart in these rift basins, they fill in with sediment. If you have older parts of a continent where there are really old pre-existing rift valleys that are no longer active, you may fill in the area with sediment as well, just because it's created sort of a sink on the landscape for water to flow to. And then if you are an environment where there's along a passive margin where there's no active tectonics, right, through time, the normal faulting along the edges of the continents, right, is just going to create this basin to fill in with sediment and deposited from rivers and in the shallow ocean, okay? So just some examples of what I'm talking about here, right, is if you look at the Himalayas and then northern India, right, this is the massive Himalayan mountain belt, right, this part of the image, and it is creating a local depression here that is filling in with sediment, and it's draining water towards it. The area of southern India is slightly more elevated because of this effect of subsidence from the weight of the overlying mountains. A rift basin, right, would be like the basin and range province of the western United States, right? So these mountain ranges, these long linear chains of mountains, are forming by the extension, the pulling apart of North America, and it creates these large basins in the middle that fill in with sediment. So like Lake Bonneville, that big Ice Age lake that tripped up a lot of people on the first midterm, those lakes are forming in a continental rift valley, okay? And so they fill in with sediment through time. And then intercontinental basins are kind of hard to show on Google Earth because you really need to be able to see structures. But the last one I'll show is just basically the continental shelf of the eastern seaboard of the United States is a perfect example of a passive margin basin. And then why this is important, all right? So for an important thing to understand about sedimentary basins and sedimentary rocks is that this shows us the history of changes in sea level both at the local and global scale. So when sea level changes, right, you are changing the depth of water along the coasts, so that changes where rivers make it out to the ocean and where they deliver sediment. It changes the depth of shallow marine environments, so it can affect where different organisms can live. And it also controls where you have focused erosion and deposition of sediment. So when you have a sea level increase, we call this a transgression, where you inundate more of the landscape and it fills in with sediment, all right? So this would be a transgression, right, where there's a larger basin and therefore more water inundates further and deposits sediment, all right? But if sea level begins to fall locally, right, then you create less area for water to inundate, less sediment accumulates, and we have a regression. You also get more erosion during a regression, right, because you have more surface of the land exposed and it can be eroded by rivers. So this is finally like a very important concept because it tells us about changes in sea level controlled by local uplift and subsidence, so changes in tectonics in a basin. And then it's also controlled globally by the volume of water in the ocean and the arrangement of the continents. So basically, like, how is like the shape of the coastline controlled, right? So just by the volume of water on Earth. So this is, may seem highly technical, but this is like pretty important science in sort of two divergent directions, is that by understanding this process of transgression and regression with sedimentary sequences, this is what facilitated much of the exploration of oil. And at the same time, as oil geologists figured this out, they were also beginning to piece together changes in global sea level that were related to past changes in climate. So, in some ways, this is a really good example of how scientific knowledge, is a tool, and it can be used to understand very different things with very different implications. So, sorry I had some technical difficulties today. I don't know what happened with that one slide. It literally just disappeared. But have a good weekend.